right now. Can you guys hear me now? Can't hear any of you folks.
Yes.
Yes.
Right. You missed a riveting conversation where we tried to figure out the day was the day Marty McFly went back in the future on October 5th, but it turned out to be October 21st, Tyler?
Yeah,
2015. Okay. No, that did. So, no, he goes in the future. He leaves. Never mind. It goes. We can discuss Back to the Future later. Definitely seems more appealing than this stuff right now. No, this is fun stuff. All right, we got the 3 T's here today. Tuesday, as in tomorrow, homework. Number 6 is due by 6 p.m. Yeehaw. And some people didn't get their quiz in. They say, oh, no, my quizzes, can I turn in late? No, I can't turn in late. I'll give you more quizzes. Here comes quiz 7. Also due by 6 p.m. So it should have gone online this morning when some people in my classroom are about ready to go to bed, it seems like, but I can check it out. But it should have been popping up. I know it popped up in one class, doesn't mean I got them all set up. So hopefully you guys, well, I'll find it really fast if it's not there. Thursday. Caffeine, lots and lots of caffeine. It's okay if I'm not gonna say, but if you ever come to class a little bit late, it's okay by me. Just get here if you can. Homework number 7. Uh-oh. Somebody wants in. Ding ding.
That's the noise.
That's the new noise.
What a great update.
It's so cool. I mean, I'm glad somebody, and it clicks on a little. If you guys can't hear the fun we got on this stuff, we got 2 little new chimes. We have a chime when someone wants in, and then a chime when they actually join the room. So, and I just got an update this morning. So somebody got paid a lot of money to do that little ding ding. That's pretty. We should, actually, we do actually need a chime for that. I don't think there is a chime for that, because when I see poor chat people down there, oh no. See, look, I have, well, you guys can see, I have nothing here to give me a chime when some poor souls, basically you guys just keep chatting away and eventually you get my attention. I look over there. So yeah, we need a chime for that too. That's coming in an update. You gotta, yeah, you gotta have a reason to keep your job, So anyway, homework number 7 is also out now. Hopefully, if quiz 7 is, well, they should both be out at the same time, but it's due by 6 p.m. Check it out. And you're going to hear another little ding ding. Here it comes. Welcome to the room. All right. They'll have voices here soon. All right. Whoa, it's a great world we live in. Okay, so you got homework 6 due tomorrow. You got quiz 7 due tomorrow. Holy cow, you got homework 7. Remember, though, this is all completely, well, the quiz, you got to get so many points. Some of you haven't really been keeping tally at all other than on the score. The grades, the grade book keeps track of it, but probably a lot of you have already got your 10 points. So I'm just saying, if you're busy, then be able to do these things maybe for the exam to familiarize yourself, but don't let these things, remember, homework is completely optional this time. It is for some bonus, but don't let that stand in the way of something more important for you out there. So I throw a bunch out there just so hopefully you guys can pick them up to get those points eventually. Today, much more. Well, we're going to do much more of Newton's second law throughout the week. I hope to finish it up by Monday, or by Friday, if anything. By Monday, we'll be doing that. We'll move it into work and energy. I don't think we'll do the law of gravitational attraction this year around. It's condensed year. So we'll work more with Newton's second law, and we'll finally introduce the Newton's third law of motion. And from this one, to get you guys excited about sticking around, we'll even get to watch a video. And the music set to, I always try to put music with the video to watch, so the clips, they got something with them. Land of Hope and Glory. Has anybody ever heard the tune Land of Hope and Glory? The other class actually got it. Couldn't believe it. Land of Hope and Glory. You know what better as maybe Pomp and Circumstance. You ever heard that one? The graduation tune. It's actually the Brits. It's like their super national anthem. It's not their national anthem. It's unofficial, but it's a real patriotic song. They really get going into that stuff. Matter of fact, when you hear the song, you'll hear the Brits eventually chime in and start singing it. All right, so how do we get to today? Well, last Friday, we did Newton second. And, oops, helpful if I put the second there. And that's F equals MA. But we just did it in 1D for one force. You know, just to start wading in those waters because it's going to get, you know, it's a basic equation. We're going to be getting really hectic stuff in here. We're going to get all kinds of forces. Oop, here they come. All right. And 1D for one force. Today, you can probably guess how we're going to do this. We're going to step it up. Multiple forces in 2D. But they're given. Okay, they're still given to you. On Wednesday, we'll have multiple forces, and I won't give you all the forces. It's just some of them you just got to know they're there. We're going to talk about special forces on Wednesday. If you're familiar with it, like weight's a force, and you just, if an object's set on the earth or near the earth or near an object surface with a gravitational field, it will have weight. So you just always got to know there will be weight here, and you got to put that in there. So in these today, I'll be spelling it out. Here's the forces. Here's all these forces acting on it. But on Wednesday and from there on out, a lot of the forces won't be given to you. Some of these natural forces. If there's a frictional force, it'll be obvious. So it has to be, I should say obvious, but it's got to be told as a frictional force. But there won't be a drawing with an arrow for you for the frictional force. You got to figure out which way to draw the arrow. So of course these are all vectors, so it's very important you get the direction of the arrow completely correct. So that's what we're going to deal with today. Just F equals MA, F equals MA, F equals MA. That's what we're going to do Wednesday. That's what we're going to do on Friday, probably on Monday. Even when we get away from, like I said, a lot of the future stuff is based upon Newton's second law. So when I derive an equation, or I made a little piece of it, I made the full bank, so we got to use Newton's second law to get this vital piece of information we need to complete this new part of this new problem, this new concept. So we'll be using Newton's second law. They'll be popping back up it'll be always turning up, just like a bad penny, as the old expression is. But here, talk about Newton's law to get us going on it. Those are two space shuttle launches, and I can definitely tell you the one on the left is one of the first two launches of space shuttle. And I think it's the inaugural one on April 12th, 1981. If it's not, it's the one that's a few months after that. And of course, there's going to be a difference. And the difference is, if you look, that external fuel tank right here is a different color. This is, of course, white. And these are probably you're much more familiar with because every space shuttle launch was with these, except for the first two. And it's more like a burnt orange color. So the question is, why did NASA change the color on their external fuel tanks? I mean, ooh, it looks nice. I think it actually does look a little nice to have a little mixed up, little combination of colors versus all white. But yes, does anybody know why they changed the color? Why they? Yeah, Will.
It was easier to find.
It's easier to find that color? In a way, it was easier to find in a way, but it's something else. There's always a reason for something. Everything, I mean, seriously. Samantha, why are you taking this course?
It weighed less.
Yeah. Okay, you've actually got the answer. Samantha, I want to know, Samantha, why are you taking this course? Because it's fun, right? Yeah, come on, dude, why are you taking this course? It's okay, say it. You have to, and you have to because you're going to take this, you're going to sit through this torture and this agony of physics, because at the end, when you pass and you get the A and you go on in life, you're going to do what? You're going to get what out of all this? All this torture today will be worth it because you're going to get what at the end?
An A.
And beyond the A.
A degree. A job.
A job, and that job is going to give you
nothing.
We have a very pessimistic
Stress.
person out here. You're going to get lots of money, and you're going to be retired before you're gray like me, and you're going to have a great life, all because of this agony you're going through today. There's always a reason for something, and the answer's been given out there. It's weight. It's weight. NASA used do something for a reason, and NASA was painting the first two of these guys, and I've painted, if you've ever painted anything before, I've painted many barns for my dad. He said, hey, son, it's been a couple of years, go paint the barn at the three-corner patch. Ugh. So you load up lots and lots and lots of heavy buckets or containers of paint, and you lug them up and down ladders, and it takes forever to paint it, and you know you're going to be back in a few years. This external tank was not reused. It will burn up in the atmosphere of the Indian Ocean without even completing one orbit. So it'll get the shuttle go into space and in its orbit. And so you have these rockets which supply you with so much thrust. That's the force, F. And if you want to get your mass up to a certain orbit, well, you can either you can waste some of that thrust, some of that force will go into lugging 500 pounds of paint, which won't even be used or reused again, it's just going to burn up. Or you can just save it and don't paint the thing. I mean, just keep its natural color. Don't waste your time, don't waste your money, and don't also waste your rocket fuel on that 500 gallons of paint. Instead, 500 pounds of paint. Instead, you can like supply a few extra things on board the space shuttle, like maybe some air for these guys, or bring another woman or two into space, another couple astronauts, some extra food for them all to eat, extra science experiments. So yeah, it was just a waste of all this money, which is you can use it for something more valuable and it saved them time. So they stopped paying the external fuel tanks right off the bat. These were just basically they made those before they first launched the first shuttles. But these guys, after they started production, they kept them in that orange color. So it's all a matter of weight, because that came into a force. And force is money for NASA. All right, so let's do an example. I'll do an example. And then we'll get you guys going on that worksheet we had on last week. We're still working our way through it. So here's an example of multiple forces in two dimensions. Two people pull on a stubborn mule. Actually, a stubborn mule's collar. So the collar is around the mule. So it kind of makes it where you can see, okay, the mule's going to be able to exert a force on the collar as well. So as shown. So a lot of these problems from now on, at least in the force in Newton's second law, a lot of information won't be given necessarily in the writing. So be careful if you haven't done these before. When they say there's a figure, you see there's a drawing there, including like my homework assignment. Look down there and see there's some more information in those drawings that won't be given in the writing, which you'll need. Specifically, the ones I always put down usually is the angles. So angles of force or act. It's a lot easier to write them down there versus in the writing. Okay, so these people pulling a stubborn mule's collar is shown. It's coming up. The mule, stubbornly, because it's a mule, negates their efforts with a force on the collar such that the collar, and of course what the mule's interested in, so the collar does not move. It just sits there. Find the components of the force by the mule. Okay. So let's draw that drawing I said would be there, that figure. Something shown. So this is an overhead view of the situation. So we have positive x and positive y. So I know positive y usually is up to this point meant vertically, but this is you looking down, so y now is just, it's like a forward motion. Forward, and x is left and right, y is forward, and if negative y, it's backwards. We don't know anything about those forces. We need to look at our drawing for that. As F1 has a magnitude of 120 newtons. And it's located at this angle here, which is 60 degrees. Meanwhile, our second force of the day over here, 80 newtons, and here's this angle. I said the day would come where not all angles would be measured from the y-axis or the positive x-axis, and this day is here now, definitely. It's just sometimes more convenient, and I'm going to get used to it. I'm going to show it right now so that when you start looking extra problems in the book, they'll do it like this too. It's really cumbersome to write the true angle, which is 105 degrees. You got to drill a whole arc around here. And every time I did it, I had to make sure I had enough room. I had to space my arcs out. Sometimes I didn't do a good enough job from class to class. So it's a lot easier, obviously, having these angles spaced like this. But now we've got a problem without that true angle from the from the positive x-axis, what is a 105 degree angle. We got to be very careful using this angle because we know he's not going to give us perhaps our correct signs for, at least when I say signs, S-I-G-N, positive or negative for the your components. We'll always give you the positive one. The question is, do you need the positive one or not? And this here object down here, we're pulling on this, your collar. And I always like to take a guess where I think that mule's going to be doing it, or where, what I'm trying to solve for, what the answer should be. Some of you in the homework problem, the last homework problem we did, actually not the last time, the last one I graded, it was that last quiz 4, it was an old one. And it asked for the, that was the hot potato game, 1D hot potato. And it asked for, you had to figure out the speed at the person had returned the ball at. And some people did it, and they solved it, and they found out their final velocity or final speed was greater than their initial. And it was, this object was going against, it was actually slowing down because of the acceleration. And they had the acceleration wrong. And because of that, it sped up. When, if you had an idea it should slow down, maybe it would have been a red flag. So always a good idea to kind of have an idea where this answer should be if possible. And I'm going to guess the mule is going to go down here. Now, I'm going to guess wrong. I know that now, but I'll keep it here. These two yahoos are trying to push forward, pull forward on the mule. So the mule's obviously got pulled backwards. So I expect he has some kind of negative y component. Now, what about the x? I don't know. This force is bigger than that one, but they're at different angles. So I just kind of just guess here. I expect it definitely have a y axis or y component, which is negative, but definitely the x component could be either way. We'll find out. Right, so, and just a guess here. Saved a few of you on that last quiz I graded. All right, so keep that there. So how we do these? Well, you've never done before, you might as well just mimic me. If you've done before, you've got probably your own method. But we just use Newton's second law. And since the vector was, when I first introduced Newton's second law, I said we can break them down, their components are right. So the sum of the forces equals mass times acceleration. You can say the sum of the x components of the forces equals mass times accelerations, x component. And the sum of the forces in the y direction, the y components, equals the mass times the acceleration y component. Right? So in other words, what we had to do is I like to write them side by side like this. If there was a z1, we'd have a z as well. F1x plus F2x plus F of the mule x equals MAX. And then you just mimic it over here, except the x's all become y's. Right. Now, the mule in this case doesn't, well, nobody moves. The people aren't moving, the collar's not moving. That's a really important thing. So if the collar isn't moving, that's the collar with mass m, guess what we know about those accelerations? There's 0. So you got to be careful about this. It's always great when you can write zeros, but you have to make sure, am I justified? So the acceleration equals 0 when nothing moves. And we're pretty good with that one. We're okay with that. But also, just throw this out here now, also equals 0 when the object is moving. Okay, it could still be moving. You can still have acceleration of 0, but what's the magic word? How can an object move and have no acceleration?
If the velocity doesn't change.
That's right. I like that echo mic effect there on whoever that was. That just sounded to me like an echo, like a voice from above. Also, the acceleration. Where you sitting at?
I'm sitting in the Soldiers and Sailors Hall, so it's all echoey and shit here.
Wow, that's pretty cool effect. That's pretty cool. All right. It sounds like Zeus talking, or God is talking to me.
Yeah, I understand the echo, but what about the shit?
God from above says, well, this is equal to 0 when velocity is constant, right? So those are going to be like little key things will be in the reads. That's unfortunate. They want to make sure you pick up on that. And it's also make sure you understand the concept of acceleration. So if the object's not moving, yeah, acceleration is 0. I get that one. But also if they state the object is moving with constant velocity, that also means acceleration is not moving. Because the only reason you can change your velocity is if there's an unbalanced force on you. So if you know there's no unbalanced forces, that means your acceleration is going to be 0. Right? So be careful about using the zeros. All right. Remember, as a matter of fact, the handouts today, there'll be times you use zeros for none of them, for AX or AY. There's times like this one right here where you got AX and AY both equal 0. There's times when one of the accelerations components, let's say AX, does not equal 0, but the Y one will equal 0. And we'll see that pop up a lot on Wednesday. Right? So you got to be careful where those zeros go and if they even go at all. And once you got this written in the FX and FY stuff, of course, that doesn't help you if we got forces like we have here. This isn't F1x, that's just F1. Well, how do we make F1x? We go all the way back to chapter 2. F1 cosine 60 degrees. Let's just write that. That's that. And then I usually, in the other class, I wrote theta 1. I actually went back and put it theta 1. We can just keep the angle. I'm going to keep a little gap here. Here's F2, and he's cosine of 75 degrees. But we got to be careful because 75 is not a real or not a proper angle, not measured from the x-axis, the positive x-axis. So you have to look at your drawing if you're going to use this 75-degree angle. And you got to say, is my x component negative or positive? He's in the second quadrant. So, Alex, positive or negative? Negative. That's right. It's not good when you are, the treasurer of something or a financial advisor to go back in the books and start adding negative signs willy-nilly or pluses. You don't want to cook the books. But in physics, it actually is okay because you're correcting for I shouldn't call it an error, but from the fact that you measured the angle efficiently, but not from the correct angle. So you got to go back and stick a negative sign for applicable, okay? Now, if you're one of those guys who like to see the 105, that's good for you. You've gone to all the work to do those big angles. Don't put a negative sign in here, right? Keep it a positive. Your calculator will give you a negative sign as soon as you say cosine 105. Boom, out comes a negative sign. So don't make an error by going through all that hard work and negating all that by putting 2 negative signs in there. Right? I don't know what the mule's doing, so he just has left his FMX. I'm going to let the math solve it for me. And on the other side, I got the same format. Sine 60. I'll leave it a blank here. Okay, once again, you gotta look at it. Anybody out there in virtual world? Is the y component for F2 positive or negative? Don't say anything. Shh, quiet. See if they come back. They're
It's
probably.
positive.
It's positive, right?
God says it's positive.
God says it's positive. It is. God is right about that. I'm gonna burn for that. Okay, but that's okay. I'm a Cubs fan too. I hear the Cubs went out fast. Check the baseball stat. Hey, I think the Cubs are in the playoffs. No, they're not. Found out they were, but I didn't check them fast enough. They were here and gone. All right, so I guess I should have substituted my magnitudes here, but okay, I can do that now. Minus 80 cosine 75 plus fmx equals 0. Okay. There we go. So each equation's got one unknown. You just solve for it. I guessed wrong about the mule as far as this x component goes. I'm not too disheartened. I look back and I say, yeah, I could have made a better guess, but looking at those two vectors, F1, F2, but I didn't. Okay. Okay, being off. This one here, I better be right about. This one, it better be negative, and it is. There you go. My two components. That's basically all we do in this class for next week plus. I mean, that sounds easy. Sign me up for this class. Of course, we're going to get, like I said, sometimes there's forces which you got to inherently put in yourself and not stated, like weight, like I said, direction, which direction is friction action. You got to figure that out. Well, even if you guys are familiar with normal forces and stuff like that, that's popping up too. We got to worry about those. And so it's going to definitely add spice to our life. Sometimes we solve for the forces. Sometimes we know the forces that we're going to do in the handout that's coming up right immediately as soon as I get done yakking about this. And we solve it opposite. We go in reverse. We find the accelerations. Usually that's the name of the game. Sometimes, though, if we want to, we can take those accelerations and say, okay, now we go back to equations of motion, provided we can. If the forces stay constant, then the acceleration will as well. And you can say things like, oh, where will the object be after 5 seconds under this acceleration? How fast will it be moving? Blah, blah, blah. We go back to chapter 3 at that point, 3 and 4. Right, so that's it. Let's see if you guys can do it now. So we're going to be working with this sheet. I know it says problem number 3, but I know if you counted, you said, we did 1, 2, and 3 on Friday. You're right. And then the magic of Microsoft Word, I guess they need an update, is when I redid this and started putting more problems, somehow I hit a tab wrong or something. So this is actually the 4th problem. But hey, just look for the blocks, okay? So we can do 3, 4, and you can probably do more than that, but we can do 5. Yeah, we're going to do, I'm surprised it didn't come up at 7 or like a Roman numeral 3 or something like that. We can also do problem 5. I say redo problem 1. That was my typo. So it's actually redoing the 2nd problem, please. You're redoing this guy. And some people ask about this one. When you do problem number 5, act like problem number 4 did not exist, okay? So that's why I said there's a 3rd force. I call it F4. And he said, well, I already had that 3rd force. No, I was in problem 4. Problem 4 never existed when you get to problem 5. That makes sense. If not, we'll figure it out as we get there. There you go. I'm going to wander around the room in here to take a drink of tea. And if you got any questions, I'm going to put the chat window up here. If you can chat, if you can get the voice of God or something like that, you can ask me and I'll come over and answer the question. Otherwise, get them done in about less than 10 minutes. We'll move on and fun. All right, gang. So we're gonna run through these fast, but show you the solutions. Because I don't know where everybody's at out there in virtual world, and since these recordings have to go out for the people who asynchronously will watch the videos later, I can't assume they're going to get it right either. So unfortunately, I'm going to walk through them all, which is good, actually, good practice for everybody to see them. There are several ways to write them. As far as vectorially, when you write vectors, you can work with the i's and j hats at the same time, separate, but nonetheless at the same time. Or you can do them like I do, and just work with the x's off to one side and the y to the other side. And the trivia question for today is the class we talked about for the guys in class. today the Nobel Prizes were being handed out in medicine. Tomorrow, physics gets handed out. So I had to keep my phone near my bedside so I can get that call in case they call me from Stockholm. They call it Stockholm time early in the morning, which is extremely early for us in the United States. There's one requirement. If you win a Nobel Prize, you know there's a few things, but one of the major things is to win a Nobel Prize, this has to be, you have to be in this condition. Does anybody know what the condition is? Living is absolutely right. You have to be living. You have got to be able to answer the phone and say, I accept the Nobel Prize. Then you can die. And they will still give it to you posthumously, but that's the only posthumously way you can do it. They won't award them until December. At Alfred Nobel's birthday, I think December 9th. That can't be, it's my son's birthday, but it's actually very close to that date. So you have to actually be alive to accept the award. Only one time was that violated, and they said, oops, we missed it. They didn't miss it. They just did it because look up medicine, Nobel Prize, posthumous award. That they had to give it to that guy that year, and it was in the age of the internet. So it wasn't like, oh, he died, it's 1950, that we didn't read the newspapers for a week or something like that. They knew, but they gave it to him, and they should have given it to that poor guy. So anyway, back to this. All right, so the first one, we want to find the acceleration of our block with this mass, or this mass of this block with these forces acting on it. So just break it up into the components. Sum of the forces in the x direction equals m times ax, right? And we're always seeing this. I've seen this happen now in 2 of the 3 classes. Mass is a mass. There's no x component or y component for mass. It's just 4 kilograms no matter what. Okay, mass is a scalar quantity. You never break it up into components. So you replace the summation by saying F1x plus F2x, and we're done. There's only 2 forces acting on this block right here. That's all we've got. Equals 4 kilograms times AX. Not big on the old units, but I made a mistake here. And then the mistake was I can get confused really easily. I've got so many 4s running around here. So I should keep the 4s with my units, like, what 4 goes where. Once you got this far, you do what we did with the mules. You've got to find your x components. With the mule problem, it was tougher because I had to take the magnitude times cosine of whatever angle. I had to make sure the angle was the proper angle. If it wasn't, I had to make sure I had a negative sign. You'll live for these guys when they're in the I hats, J hats. I know it's sometimes still confusing to some of you, but you really want it like that because the problem's already done the math for you as far as breaking it down the components. You look up here for the x component of good old F1, and it's a number in front of the I hat. Or you look for a number in front of the I hat for the F2. You see, but I don't see an I hat. You're right, there is no I hat. So guess what that, it's just a big old goose egg, 0. And I get 4 kilograms times AX. AX equals 4 newtons over 4 kilograms. AX equals 1 meter per second squared. If you know the forces in newtons and the mass in kilograms, acceleration's got to be in meters per second squared. Right? Kind of short on space here, but I can tuck it in down here. I guess on the exams you don't have to worry about it. If it all goes multiple choice, I'll never see your work, but you should try to keep it as neat as possible for your own safety, your own sake when you look back. Same game. This is a mule problem. Just only 2 forces here. Well, the acceleration doesn't equal 0, but it's the same setup. F1y plus F2y equals m times ay. You look for things now in front of the j hats. Like I said, now in the mule problem, you had to break down components. And this one is similar, but it's already given to you. There is no j hat for F1. And look at F1. It looks like it points completely along the x. There is no y to it. No shocker, it's 0. Plus 2, but newtons there, equals 4 kilograms times AY. AY is 2 divided by 4, 0.4 meters per second squared. If you like to write it like this, there was no reason to do that other than the fact that the answer was stated that way. acceleration equals its x component plus I hat plus its y component, j hat. So you just stick in your right numbers. 1 goes in here, it's going to be I hat plus 0.5 j hat. Ta-da, either one. There you go. Okay. Second guy, it's the mule problem again. You set it up the same way as before. I mean, as all these problems are will be done. And I've got plenty of room now, so I'm going to write them side by side like I like to do. Hey, nobody's moving. No acceleration. So 0, 0. F1x plus F2x. Now there's a third force. I'm trying to find that third force. So this will give me my x component for him, and here's the y. You look back up here to your forces. F1 is got a 4 for his x component. F2 still got nothing. F3x is what we're trying to find, and all equals 0. So just keep on solving for this last step. And since it is, these other guys are in newtons, this guy's in newtons. That's your x component. Play the same game with your y's. F1y was 0, plus a 2, y component of the second force, plus F3y equals 0. F3y equals -2. Okay, let's just keep the fun going. I know some of you in your head right now is, yeah, we're waiting for that fun to start anytime now. I know. So the last guy, like I said, we'll be doing problem number 3, and our second number 3, and we act like number 4 never existed. So we have a third force, another third force added to the first 2 that will give a net acceleration of this as stated. So we got to be able to read that and figure out where that goes mathematically. Well, I can write it right now. A equals AX I hat plus AY J hat. Okay, well, what are they telling me? I've got a y component, so I got an x component of 4 along the negative x-axis, so that means it's -4. And there is no j. It doesn't say anything about acceleration along the y-axis or the j component at all, j hat. So it's just 0. So I just have my acceleration equals -4 I hat. I'm going to be able to find the force in this one like I did before, but now not all the accelerations are going to equal 0. Sum of the force in the x direction equals max. Sum of the force in the y direction equals may. What forces act on the object? F1 and F2. And like I said, F3 doesn't exist from that previous problem, but F4 is a new guy. So F4x. And that gives me a 4 kilograms by mass, and the acceleration in the x direction is at -4. Meanwhile, in the y's, same story, it looks like, except it's all y components, but the acceleration is 0 in the y. Nothing there. Plus 0, if you want to call it that. 0 j hat. Plug in the numbers we know. F1x is 4 plus 0 plus F4x equals -16 in kilograms times meters squared, newtons. F4x equals -20 newtons. Got him. F1y is 0 plus 2 plus F4y equals 0. F4y equals -2. So we're just playing around. Sum of the forces in the x direction equals m, straight m, times ax. Sum of the force in the y direction equals m, straight m, times ay.
I calculated that doing the acceleration first and then just multiplying it by the mass afterwards. Is that also valid?
Oh, to get which part you're trying to find what? The component?
Define the forces, yeah. I did the acceleration vectors and then just multiplied the mass afterwards. I got the same answer.
Okay, okay. I was gonna say, as long as you keep them as components and you multiply by yeah, that'll work out. Okay.
Okay, thank you.
The key thing is when you put those zeros in there, like that's why these three guys are sitting here. First problem, obviously, the acceleration for zeros. We don't stick in zeros there. Second one, problem number 4, the object was not moving, not undergoing any acceleration, aka, so we were able to put 2 zeros here. The way this guy was written, one guy was a 0, the other guy was not. So we're going to see that happening a lot. You know, when we talk about objects sliding along the floor, the vertical axis will have no acceleration, and the horizontal one might have an acceleration. Okay, so okay, all right. So that's that in a nutshell. So let's talk about Newton's third law. If there's no questions about it, nothing else. I'll see chat stuff. Nobody's chiming in. I gotta switch the, sorry you guys in class, and switch your screen to be bigger. Just about there. A little video here as soon as I talk about Newton's third law, and that's it. Oh, that's like page 4, 5. Come 6. Newton's third law of motion, also known as the action-reaction law. I also like to call it the sibling laws too. If you've ever had an older brother or sister, still do, maybe when you were younger, you're familiar with Newton's third law, at least a partial analogy to it. And I'll explain that in a second as soon as I state what Newton's third law actually states or says. Whenever one object, we're going to give this a very imaginative name called number 1, exerts a force on another object, we'll call that number 2, then object number 2 exerts a force on object number 1 that is equal in magnitude but opposite in direction. So I had a younger brother. I tried to push him. Guess what he did to me? Push back. All right. What was that? He felt, yeah, you're right. He was a lot younger than me. Yeah. So for a while there, I had him, but man, after a while, I had to realize, you know, I might not want to be pushing him around anymore. So especially he worked a lot more on the farm. He's a stronger guy, bigger guy than I was. So, but for a while, I had a little advantage. But anyway, in the strict sense of Newton's law, if you push on somebody, they will push back in an opposite direction. And if it's strictly Newton's third law, equal but opposite. Of course, people usually, you know, in real life, they want to, you know, agitate the situation, step it up a notch, but that's not what you should do. That's not what Newton's law does. So I'm going to try to draw it with a drawing here, which I need to work on my stick figures. So I get somebody trying to push on a wall. I don't know what Exactly, if it looks like they're pushing up, they're supposed to try to, it looks supposed to indicate they're pushing. So they push on this wall, and they, this is the force direction you apply to the wall. And we can give it a little bit more of a symbolic representation of F of Y for U. When I say U, I don't mean the letter U. It's unfortunate. It means the word Y, O-U, on W. So U on the wall. But by Newton's third law, it states that there's a force of the wall on U. Put that in some kind of little notation. W on the letter Y represent U. So vectorially, Newton's third law is this. This force of U on the wall equals negative, opposite direction, of the wall on U. But regarding magnitudes, the magnitude of the force of U on the wall equals the force of the wall on U. First time I saw that, I got really confused. It looks like those are the same equations. Why aren't they, and yet one's off by negative sign. It seems like it looks so contradictory when you first see it. And the reason that this guy's negative, this is a vector quantity. This negative says it's going in the opposite direction by these arrows. But as far as how big the number is, if you actually had a force meter, you can see, okay, how much is the wall pressing against you? And I don't care about drag, I just want to know how much it is. Basically, like a scale. Weight, scale measures a force. It's a weight. And the scale would read, let's say, 20 pounds or 20 newtons. And if you can now apply that, okay, well, let's see how much force I'm applying to the wall. It would also read 20 newtons. So the two forces that have equal magnitudes, the numbers would be the same. But if you now say, well, which one, what direction are they pushing? They're directed in opposite directions. Okay, that's the good old Newton's third law, which is going to be really, really valuable when we come up and start talking about things like normal forces, which is going to be on Wednesday. If you dealt with forces before, Newton's laws, maybe you've heard of those. Sometimes it's really important to keep Newton's third laws so we actually can figure out forces such as that. But we also have to be careful. Here comes a word of warning, which will get a few of us. None of us, but it usually gets somebody. We will continue using Newton's second law to solve problems. I mean, this, basically we're just going to be doing, getting us to the point where we can use the equation of motion again, or maybe radial acceleration. But the thing is, now we can actually figure out what actually gets us to that acceleration. We don't have to no longer have to say the car is accelerating at this certain acceleration or it's moving at a certain velocity. We can figure that out. Just give me the forces, and I can do that. Which you engineers going to design bridges and building stuff like that. It's extremely important to be able to do that. So we'll continue using Newton's second law to solve problems. But with every one, you have to only use all forces that act, here where I should put the word only at, that act only on the object in question. This is the one you want to find the acceleration for. The one you're trying to find, I'll say perhaps, its acceleration. So the problems today we did, the little ones, the mass was 4 kilograms. That was the mass I was interested in. I want to know what forces are acting on that guy. You think, well, the 4 kilogram mass, it's got to be doing something. It's got to be, it's got gravity. It's got a gravitational attraction. It's very small, but it does have one. It's also pushing against you. If you push on that, according to Newton's laws, you push on the 4 kilogram mass with F1, it's going to push back. I don't care about those forces. I just want to know what forces are acting on that object. The trap is you start looking at this Newton's third law and say, oh no, well, these two forces equal 0. They add up. You're right, they will add up to be 0. But when it comes to Newton's second law, it's not all the forces, it's just the forces acting on a certain object, the object I'm interested in. I want to know that mass for that little m, what that little m is going to be when we put the mass of whatever object is, that's the force I want to know is acting on that m. So if I'm talking about the wall, I care about this line right here. I don't care about that one, that red one I just covered up. It's the force the wall applies on me. I don't care about me. I care about what's acting on the wall. If I cared about me, what forces are acting on me or the stick figure, then I care about this force. I don't care about that one. Okay, so you never write these. If you do Newton's second law, you'll never ever write these two forces together. You only write one or the other. Right? So leaves you just enough time. When you talk about Newton's third law, does anybody know the standard videos you got to show? It's almost decreed by the Constitution of the United States. When you think Newton's third law, action reaction, what's an object which it shoots out something really, really fast, and by Newton's third law, the object it's shooting out gives you a boost in the other direction. Was that?
I was thinking of Newton's cradle the whole time.
Newton's cradle, the little balls that go back and forth? Yeah, that's a good energy conservation one. You can always apply it. I was thinking of something a little bit bigger, and here's what we're going to do. This is going to finish up the class. It lasts about 6 minutes, which is how long we've got. We got to hear, listen to our hope and glory now. Here we go. Hope and glory. Just sit back and chill out. Here we go. Hope.
Five, four, three, two, one. Whoa! Awesome!
Here it comes. Here we get parachute. Mars overtime. Uh-oh. Uh-oh. I never thought I'd see the day when we actually had commercial people, commercial companies making rockets, and only that, returning them back to the Earth like SpaceX is. Maybe you guys someday will work on something like that. It's if you want to talk about F equals ma, that's the reason they land them on the barges in the ocean. They go, that just sounds crazy. It's all about money and what makes it easy and what makes it possible to get those rockets back the safest, cheapest, and quickest way for those guys. Never thought I'd see the day. Hopefully, if you do work for those guys, you won't be like those poor scientists. You saw that one control room in there after that Russian rocket blew up. They're just looking. Oh, what can you do? The camera's on you, just look a little disappointed. And we'll launch another one. But like I said, you guys have a nice day. Good luck to you if you launch rockets one day like that. Take care. Have a good day, guys.